Hello, welcome to CSC7132 Operating Systems and Networking. This is Brady Chen. Now, in Module 4, we're going to talk about concurrencies. Well, multiple processes are competing for the shared resources. Now, the first section, section 4.1, we're going to talk about the process interactions. Section 4.1, process interactions. Now, in a multi-programming environment, multiple processes can execute at the same time. Now, this is called concurrency. Now, concurrency may be achieved by time sharing for the system with single CPU. Now, in that case, there's only one CPU, and the operating system scheduler going to actually schedule the processes. Now, each process is going to take a turn to use the CPU. Now, when the system contains multiple physical CPUs, now things are slightly different. Now, the scheduler can schedule one process to one CPU, the other process to the other CPU. Then this time, we can achieve the true parallel computing. Okay. So now in either case, when concurrent processes access common data area, then we must be very careful because the data must be protected from simultaneous change by two or more processes. Now, this kind of situation is called a race condition. Now, let's take a look at the example. Suppose I have a process P, and I have another process Q. Okay, each process is going to execute some statement. Okay, now one of the statement is x equals x plus 1. Okay, so x is a variable. So that means after you execute the x equals x plus 1, then you increment the value of x, right? So then another process Q have the statement x equals x plus 2, and then plus some other statements. Now in this case, the statement is going to increment the variable x by 2. Now, if one process executed before the other, say the CPU pick the process P and execute the process P, right? Until it's finished. And then the operating system pick another process Q and then execute the process Q. Now, if things like this happens, everything should be okay. Okay. Now let's assume that the variable x is initially assigned with 0. So x equals 0. Now, this is a shared variable, right? So this is a common data, okay? So which can be accessed by both P and Q. Now, if P is executed before the process Q, then there's no issue. Because after you execute the process P, now what's the value of x? X becomes 1, right? Now, and then after you complete the process P, and then you start the process Q, and after you execute the statement x equals x plus 2, then the value, what's the value of x? X actually, so in this case, the initial value is actually 1 because it's updated by process P. So then after x equals x plus 2, then the value of x becomes 3, right? So the final value is going to be 3. Now that's a kind of easy case. Now let's talk about another scenario. When two processes are executing concurrently, so two processes execute this statement concurrently. Now what happens? Now initially the value of x is still 0. Okay, let's say that's the value is still 0. Okay, now the P and the Q basically are running concurrently. So that means in the single CPU scenario, time sharing is used. So that means the CPU going to execute some of the process, some of the instructions, some of the statement in P, and then switch to Q, and then switch back. So the process P and the Q actually take turn to run. So in that case, what happens? Now, before we discuss this, we first need to realize that, for the statement x equals x plus 1, now that's most likely it's a high-level language. Now, for the machine to execute that statement, then you need to compile this into a machine instruction, right? Now, for x equals x plus 1, typically it contains 3 machine instructions. Okay, so the first one is, let's say, you're going to execute load instruction. It will load the contents of variable x into register R. Okay, so now x is actually stored in somewhere in the memory, and then you first need to load the value of x into the register, into a register in the CPU before actually CPU can execute it. Okay, so let's say it will be loaded into the register RP. Okay, so I can say load RP, comma x. So you're going to load the value of x into the register RP. Now then you're going to perform another. You're going to perform another instruction called add. Okay, so add R, okay, constant C to RP. Okay, so C is a constant value in this case. Now in this case, the constant C is actually 1. Okay, so you're going to add 1 into the register P. Okay, and then the third one is, it's called a store. Now you're going to store contents of R, P, into X, back to X. So these are 3 instructions after the compiler. So load the contents stored in X to register RP. So the contents stored in X is 0, right? So 0 going to be loaded into the register RP. So then you add 1 to the RP. So now the RP contains, the register RP contains 1, and then store RP, which contains 1, back to X. So now it basically changed the value of X to 1. So that these are the 3 instructions the computer system is going to run to perform these operations. Now, same thing for the other one. Load, let's say RQ. That's okay. So load the contents of X into register RQ, and then you're going to do the same thing. RQ. Now in this case, add 2 into RQ, and then you store the value of RQ back to X. Okay, so X is the memory space in a memory address in the memory, and RQ, RP are basically the registers in the CPU. Okay. Now, so instead of running these one, you're gonna run these 3 instructions. Okay. Now let's see. Suppose P and Q are running in concurrently, right? So then you're gonna run CPU gonna run the instructions in P, and the CPU gonna continue and run one of the instruction, load RQ, comma X, and then the CPU gonna run the next one, CPU gonna run the next one. After CPU complete these 3 instructions, the value of X has been incremented. The value in the memory has been incremented. That's fine. The same thing with the Q. Okay. Now, if the scheduler switch back and forth between P and Q, now if once the first instruction for this operation is executed, load instruction is executed, and then the second one, add, is executed, and the store is executed, and then the value of X basically changed from 0 to 1, right? And then you're going to continue, and maybe you're going to switch to process Q, and the process Q going to execute the other instructions until process Q reaches that one. But now in this case, when you load the X, the value of X is 1, and then you add 2, to the register Q, and so 1 plus 2 becomes 3. So you basically RQ contains the value 3, so it will store back to X. So the X becomes 3, right? Now that's one of the scenario. Now what about, let's see, let me erase some of the something I just wrote. Now let's see, what about this? Okay, so that's the X. So now in this case, I can also record the register, right? RP and RQ, the register actually. Okay. So let's say the CPU choose process P to run, and then CPU start to execute the first instruction for that statement X equals X plus 1. So now in that case, now initial value of X is still 0. Now in that case, the value of X going to be loaded into the RP, right? So RP is 0. Okay, and then I execute the other processes instruction. So you're going to add RP with 1. So add 1 to RP. So this becomes 1. Now, if something happens over here and the operating system scheduler decide that it's time to switch to another process. Okay. Now, for some reason, it happens that during the execution of a queue, it happens to execute the first instruction, load. Okay. Now, what happens? When you load X to RQ, now what's the value of X? I know that we have run 2 instructions over here, right? But they made a change of RP. So RP is now 1. But the value hasn't been stored in the X yet. So the value in the X is still value in the X is still 0, right? So when you load X to RQ, the value of X to RQ, you still load 0 to RQ, right? So even though the value in the register RP has been changed to 1, but that one hasn't been loaded back to, stored back to X. So X is still 0. So now let's assume that you're gonna run the next instruction. So add 2 to RQ. So now RQ becomes 2. Okay. And then it complete the third instruction in process Q for this, and it store RQ, yeah, into X. So X becomes 2. And then execute some other instructions. And then this operating system schedulers decide to switch back to process P. Now, when it switch back to process P, it can actually restore all the data in the CPU and then find out, okay, so I find out next instruction going to be store, right? I already done 2 instructions, load and add, but the next one is store. So now, in that case, it's going to store RP to X. So what is RP? RP is 1. I store RP to X. So it doesn't matter what's in the X. You're going to override it. Okay, so X becomes 1. So once actually process P finish the store RP, comma X, then the value of X becomes 1. Okay, so then I continue the next one. Now what happens? Now process P and the process Q running concurrently. And the process P execute X equals X plus 1. Process Q execute X equals X plus 2. Now, depend on the execution sequence, the result of the X is not predictable. Now, in this particular case, if I run 2 instructions for this load and add and switch to another process Q and I execute 3 instructions and I switch back, then the value of X becomes, the final value of X is 1, right? Now, that then seems to be right. Now, you can try another scenario. So let's say if I run 1 instruction here and I switch to the other process and I execute all this, 3 instructions for X equals X plus 2, and I switch back to here and continue the remaining 2 instructions for X equals X plus 1. Now you can check the final value of X in the memory. It could be different. It's not a 1 anymore. It could be some other values. Now, this is actually interesting, because if I run the process P and Q concurrently, the final value of X is not predictable. It is dependent on the time series when the CPU scheduler decide to switch from P to Q. So that's very important. Okay. So that's called a race condition. Race condition is bad because in that case, if I have 2 processes, I run this time, then the result of X is 1, and run another time, the value of X is 2, and run another time, the value of X is 3. So I think 3 is expected, right? So we assume that after the execution of process P and after the execution of process Q, the value of X should be increment by 3, because 1 increment 1 by 1, process P increment X by 1, and process Q increment X by 2. So I expected that the final value of X is going to be 3 after I complete both processes. Now what we find actually is the result could be different. It's unpredictable. Now, what's the problem? That's a race condition. Okay. Now, how to resolve that problem? Now, operating system actually use something called a critical section to resolve that issue. A critical section is a segment of code that cannot be entered by a process, while another process is executing a corresponding segment of the code. Okay, so that means we define segment of code as a critical section, and then critical section is not separable. So that means when you do the time sharing, you have to let the CPU complete the critical section as one piece before you can switch to the other. You cannot switch in the middle of the critical section. Okay, let's take a look at the next slide. Now we mentioned that the operating system used the critical section to resolve these race conditions. Now, in the previous example, for example, like if we want to actually execute x equals x plus 1, then we know that after the compiling, then this is actually basically split into 3 instructions. Okay, for this one, like let's say load the contents of x into RP for this first process P, and then add 1, the value 1 to the register P, and then store register P back to X. Okay, and then the other process Q, somehow you're going to execute x equals x plus 2, then you're going to actually execute its own instructions. In that case, maybe I'm going to load the contents of x into one of the register. I call it RQ, right? And then add RQ, add 2 to RQ, and then store RQ to X. Now, in this case, the problem actually happens that the context switching, happens when the CPU is running the instruction in these, right? So when CPU is running one of the instructions for the x equals x plus 1, and then it switches, okay, to another process, and then execute, and then switch back. Now, using the critical section, I can define these 3 instructions as just one piece, and that's called the critical section. And I can define these 3 instructions as the critical section. Okay, so that means when CPU is currently running process P, and if CPU happen to run the instruction in the critical section, now the operating system cannot switch, the processes. It cannot actually, kick the process P out and load the instruction in Q. So you have to let the critical section complete, okay, before you can switch to other process. Okay, so that's the things. Now, so for any solution to the critical sections problem, we define the following 3 requirements. So any solution must satisfy the following requirements. One is, first one, guarantee mutual exclusion. Okay, so that means only one process may be executing within critical section. Now, why we had a problem in the previous example? The problem is because, when we actually we are running instructions in the critical section, right? Now we actually suddenly switch to another process, and another process Q also run into the critical section. Okay, so now in this case, this violates the first rule. Okay, so that means when you switch away from process P, now currently, the process P is running, executing in the critical section. And then you switch to another Q. Q is also executing in the critical section. So now both P and Q are in the critical section. Condition 1 says, the mutual exclusion says, only one process may be executing within this critical section. Okay. Now, if that's the case, then this is never going to happen. This is never going to happen. Okay. Now, the second condition says prevent lockout. A process not attempting to enter the critical section must not prevent other process from entering the critical section. Okay. So that means if this process is trying to run into the critical section, start to run the first instruction in the critical section. Now, if the process Q is not in the critical section, now process Q cannot prevent P from entering the critical section. Okay, so that's condition 2. Now, prevent starvation. A process or group of processes must not be able to repeatedly enter critical section while the other processes are waiting to enter. Okay. Now, when you actually set up a mutual exclusion, the starvation may happen because the process P enter the critical section and the process P running in the critical section. And during that time, if process Q, when I switch to process Q, and if process Q want to enter the critical section, the operating system has to block it, right? Because process Q cannot enter the critical section because process P is currently in the critical section. So the process P is going to be blocked. And then after time elapse, then the operating system schedule decide to switch back to P, and P is going to continue to run the execution instruction in the critical section, and then it switch back to Q, and suddenly Q is blocked again because some other processes are running in the critical section. Now, in this case, we're talking about more than 2 processes. If we have a multiple process, P1, P2, P3, all the way to PK. So the CPU actually, operating systems, schedule and can switch these using the time sharing. So it will switch the process back and forth, So if, a process is waiting to enter the critical section, and it's always blocked because the other process is running in their critical section. Now, this is going to cause the starvation. So if you implement any critical section solution, you have to somehow figure out how to prevent starvation. Now, also prevent deadlock. Multiple processes trying to enter the critical section at the same time must not block each other indefinitely. Now, this is an interesting situation. Sometimes when process try to enter the critical section and it was blocked because another process is in the critical section. Now, then other process try to enter the critical section and it's blocked by another processes. So maybe the process 1 try to enter the critical section, it's blocked by process 2, and the process 2 try to enter the critical section, it's blocked by process 3, and the process 3 try to enter the critical section, and it's blocked by process 1. So if something like this happens, you may have the situation called deadlock. Okay, we're going to discuss the deadlock in a dedicated section. Okay, now let's take a look at a solution here. So in this case, we try to resolve this critical section problem. Now, this solution actually is for 2 processes only. I have process 1 and process 2. And each process has its own critical section. So it's not just one statement called CS, but it's actually a fraction of code we define as the critical section for each process. Okay. Now, here's a solution. So when we implement 2 while loop, so when process 1 try to enter the critical section, so they, you have to actually execute the statement here before you get a chance to enter the critical section. Okay. Now, if process 2 try to enter the critical section, you need to execute these statements, right? So now, what's the purpose for C1 and C2? So the solution actually used two variables, C1 and C2. Okay. Now, initially, both C1 and C2 are 0, set to 0. So what does that mean? If it's 0, that means, let's say if C1 is 0, so that means in this while loop, the C1 is 0, right? If C2 is 0, that means this is 0. Now, this while loop is the one that they used to control whether we can enter the critical section for P1 or for P2. Okay. So if P1 wants to enter its critical section, so it will first execute C1 equals 1 and the well width equals 1, right? So in that case, once process 1 actually enter this and try to enter the critical section, the C1 is set to 1. Now in that case, now if P2 try to enter its own critical section, then try to enter the critical section, and then P2 will find out C1 is actually 1. 1, that means it's true, right? And also, when P2 try to enter the critical section, the well weight is already set to 2. So this is a 1, and this is well weight equals 2. That's also true, so which is 1. Okay, 1 basically means true, okay, logically. So then this is a logical operation. Okay, if I have a true and true, so that means the result is true, right? So if this is true, that then the while loop, will be executed. Now that's the tricky part, because this while loop, if you look, this while loop is empty while loop, so there's no body. Now if you really want to put the body, you can put the two bracket here. So, and then without any code inside the while loop. So this is an empty while loop. Okay, empty body. So if the while loop is true, then it will actually execute the empty while loop. So it was stuck in the while loop. Okay, so just keep that in mind. And so now for process 1, it's controlled by C2. So if C2 is 1, so that means this is 1. And also if well weight is 1, so if both this is 1 and this is well weight is 1, so that means the value for this is also 1. So if it's 1 and 1, that means the result is 1, so it will be stuck in the while loop. Okay. So now the only time that the process 1 can enter the critical section is either this is 0, C2 is 0, or well weight is not 1. So either case, or for the process 2, either C1 is 0 or well weight is not 2, right? So these are the only two cases. So now if P1 wants to enter the critical section, it will set up C1 to 1. So this will prevent P2 to enter the critical section, and then vice versa. So once C1 is 1, so that means C1 is in the critical section, and the C1 get a chance. So C1 is 1. That means process 1 is try to enter the critical section, and once the process 1 enter the critical section, then it will execute in the critical section, and the C1 is still 1, right? So this will be process 2 will be stuck, continue to be stuck in the while loop until C1 process 1 complete the critical section and set the C1 to 0. So this make the first statement C1 becomes 0, so it's false. Now if I have a false and true, then this is going to give you the false. If the while loop becomes false, it will be quit the while loop and enter its critical section. Okay, so C1 and C2 are used to control each other, prevent the other process enter its critical section. Now why? The question is why we need a well weight. So the well weight is used to break the tie if both process try to enter the critical section simultaneously. Now this is actually a kind of a very special scenario. Now let me actually erase this mess and try to discuss the scenario when both C1 and C2 is 1, and how can we break this situation? Otherwise, if both C1 and C2 are 1, then both while loop are true, then both processes cannot enter the critical section. Both are stuck in the while loop. Why? So that's the reason why we introduced the while wait. Now let me actually erase this mess so we can check. Okay, let me erase this and this. Okay. Now the while wait is going to be used in a scenario when process 1 tries to enter the critical section and execute this statement, or maybe execute the next statement, and then before process 1 execute the while loop, and suddenly the operating system scheduler say, well, it's time to switch to process 2. Okay, so now you complete these two instruction statement and then switch to process 2, and the process 2 also try to enter the critical section and execute this and execute this. Now what happens? In this case, process 1 execute the C1 equals 1, so now C1 equals 1 now, right? And then execute the while wait equals 1, so while wait is 1 now, right? And then before it tried to enter the critical section, it switched to process 2, and the process 2 execute C2 equals 1. So now C2 equals 1, and then execute while wait equals 2, so now while wait becomes 2. The while wait becomes 2. Now, let's say there's two scenarios. Now, if the scheduler continue to allow the process to execute the while loop here, now what happens? So that means C1, which is 1, right? And the while wait is 2, so it's also the value true. So here's a 1, which is true. Here's a 1, the value is 1, which is true. So then it will be stuck here, right? Process 1 will not enter the critical section. Now, until the time passed, now when the time comes, the operating system scheduler says, well, it's time to switch back to the process 1 now. Now, well, these scheduling going to switch to, it will switch to that point because it's just completed these two instructions. So then it will execute the while loop. Now, what happens in this while loop? So check the C2. Yes, C2 is 1. So that's true, right? Now check the while wait. What's the value of while wait? The while wait is not 1. Remember, the while wait was executed, and assigned a 1, but after that, actually, this process 1 entered the while loop, it switched to process 2, and the process 2 changed the while wait to 2, right? So now the while wait is 2. So now you compare 2 with 1. So 2 compare with 1, so that's false, right? The value is false. So 1 is true, true and false, and this is going to give you the false for the while loop. So now this while loop get a false value, so it will enter the critical section. So this case, both process 1 tried to enter the critical section, and before it's entered the critical section, it switched to process 2, and process 2 tried to enter the critical section. So in this case, both tried to enter the critical section. Now, the while wait. Now in this case, that's the scenario that both C1 and the C2 are true. So now the while loop is controlled by while wait. If the well weight is 1, so then P1 will be blocked. If well weight is 2, then P2 is blocked, but not both. Okay, so that's the reason why we need 3 variables. Now this is actually the solution to prevent the, both the process entering its critical section. Okay, so it actually achieved the mutual exclusion. But we will find out this is really not the true solution, because number one, it only works for 2 processes, not for multiple processes. And also, you're going to have some kind of issues that the one process may block the other one, because if this process stuck in the critical section and it never actually out of critical section, and this will block the other one, because it will never switch the value C12 back to 0. Okay, so this is actually a solution, but it's not really going to solve the problem, particularly when we have more than 2 processes. Okay, so we have talked about a race condition. Well, multiple processes compete for access to shared resources. Now, this may result in undesirable situation. Okay, the solution for this is to use the critical section. So we actually provide a solution for the critical section problem, but that's not a real solution because it only works for 2 processes. We're going to discuss these solutions for the critical section problem in a follow-up sections. Okay, but first we want to talk about the process called cooperation. So we can actually use the shared, variables to create some kind of cooperation between processes. So a typical scenario is when one process produces data needed by another process. Okay, so in that case, we call this a producer and a consumer problem. The producer process must be able to inform the waiting process whenever a new data item is available. So the producer process, update the data. It's a shared data, the common data. And then once it's updated the data, the producer can inform another process called the consumer process to consume the data. Okay, so this is actually kind of scenario that the 2 processes actually work together to solve a problem. Okay, now producer-consumer problems are typically used in the warehouse kind of situation. That you can think about the warehouse as the common data, the shared data, and the producer is like a vendor who actually ship the product into the warehouse, and the consumer process is, you can think about the consumer process as the consumer that like a department store, supermarket, that they consume the product and take the product out of the warehouse. Now that requires some kind of a collaboration, cooperation between 2 processes. Okay, let's take a look at the producer and the consumer problem. Now, producer is a process, consumer is another process, and both processes are cooperate to, produce the data and consume the data. Okay, now the middle one is the area that we can put the data. That's the buffer area. Okay, now the producer first produce the data. Okay, produce the data. That's the data it produced, and then it tried to place the data into the buffer. And then once it's done, it just do another job to mark the buffer actually as full. So it's just raise the flag, say the buffer is full. And then it's going to produce the next data. Next data. And then once it's produced the next data, you cannot place the data immediately because you have to make sure you have to wait for buffer to empty. Okay, you have to wait. Okay, and then on the consumer side, while producer is producing, consumer is waiting, and wait for buffer full. Okay, and then once the consumer see the buffer is full sign because the producer mark the buffer as full, and the consumer going to basically consume the data. Okay, so first you can remove the data from buffer. Okay, and then next one, because producer going to mark the buffer as full, the consumer going to mark the buffer empty. Now once the producer see this sign, say the buffer is empty, then the producer can actually produce the next data, right? And then the consumer going to actually process the data, consume the data. Okay, so that's basically the and once it's done, you're going to go back and wait for the buffer. Okay, so it's like a one buffer. Produce the data and put in the buffer, mark the buffer as full, and the consumer see the buffer is full, and then remove the data out of the buffer, mark the buffer as empty, and then the producer can produce the data again and put in the buffer. So this is actually the cooperation between producer and consumer. It's called a producer-consumer problem. Now here's the problem from Zybook. It's exercises 4.1.1. The possible code interleaving. Okay, now we can figure out what's the various different combinations of these instructions in different processes. Now, the problem is that you have two processes. Okay, process 1, process 2. Now, process 1 gonna actually executes a sequence of machine level instructions. S1, that's one instruction. S2 somewhere, and the S3. Another process, process 1, gonna execute some machine level instructions R1, and R2. That's the sequence S1, S2, S3 in process 1, and that's a sequence R1, R2 in process 2. Now, the problem is to determine all possible interleavings of the instructions when the two processes run concurrently. So it's possible that the process 1 execute S1 and then execute R1 before execute S2, right? Or process 1 complete S1 and S2, then execute R1. So there's a various different possibility. Now the problem says determine all the possible interleavings. Okay, how are we going to do this? So this is actually a math problem, right? So let's take a look. So the easiest scenario is process 1 completed all its machine level instructions S1, S2, S3, and the process 2 start to execute R1 and R2. So that's So now we have a process 1, process 2. So you're going to say S1, S2, S3, and then process 2 start to, Now that's one order, right? Okay, so 1, 2, 3, 4, 5. So let's take a look at another case. S1 finish, S2, right? And then somehow R1 actually execute before S3. Okay, so now you have a R1 and then S3, R2. And now another possibility is S1, S2. Then I have R1 and R2, and there is 3. So that's the other possibility. So I just moved R1 before R3, and then in this case, when R1 before R3, there are two cases. The R2 is after S3 and R2 is before S3, right? So these are another scenario. Now the other scenario is R1 is executed before S2 and S3. So S1 and then R1, and then I have a S2, S3, R3. That's a possibility. And the next case is still S1, R1, but now R3 move up one position. So now I have a S2, R1, S3. And then R1 move up again, right? So I have S1, R1. Oh, I'm sorry, this is R2. R2, S2, S3. And then I move up R1 again. So then you have another scenario. So now R1 is the first one to execute. And now I have S1 and S2, S3, R2, right? And then I move R1 up one position. So I have R1, S1, S2, and R2. I move R2 up one position. And then I move R2 again, S1. Now it's R2, S2, S3. And then move up again for R2. So I have R1, R2, S1, S2, S3. I think that's pretty much all the scenarios we have think about, right? Because I cannot change the order for S. The sequence of S is always S1, 2, 3. Sequence R is always R1, R2, R2. But the S and the R can have a different orders. So how many different the possible interleaves? These are all possible. So how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 different possible interleaves. Okay. Thank you.